So in our last class meeting before the Easter holiday, we were talking about analyzing balanced three-phase circuits, and we dealt specifically with Y-Y systems, where we had a Y-connected source connected through transmission lines to a Y-connected load. I'll figure out why the screen stopped displaying up there. There we go. And we developed a single phase equivalent circuit model that made our analysis pretty straightforward. So today what we're going to do is we are going to develop some transformations to make delta connected sources look like Y connected sources and delta connected loads look like Y connected loads, so that we can use that single phase equivalent circuit to do our analysis on any three-phase system. So we've laid down the fundamental groundwork for some of these already. So let's start by looking at transformation between balanced sources. So let's start by considering a balanced three-phase Y connected voltage source. So up here is going to be my terminal A. Over here will be my terminal B. Down here will be my terminal C. Here in the middle is my neutral. So this would be VAN, VBN, and VCN. And assuming a positive phase sequence, our phase voltages for this source are going to be whatever the magnitude of our phase voltage is, with an angle of, let's call it 0 degrees. VBN will be the same thing, shifted by 120 degrees, so that will be VP angle negative 120, and VC will be VP angle negative 240 degrees. So this three-phase Y connected source also has associated line voltages. So our line voltages are going to be VAB, VBC, and VCA like so. And we can write a Kirchhoff's voltage law equation around any of these triangular paths. So if we started from neutral, came around like this and ended back at neutral, we could see that we would have negative VAN plus VAB plus VBN is equal to 0. And we could rearrange that to say that our line voltage VAB is simply going to be VAN minus VBN, which is the same as saying VAN multiplied by 1 minus 1 angle negative 120 degrees. And I believe we did this math on Thursday, but somebody hit me with what that 1 minus 1 angle negative 120 degrees looks like again. Square root of 3 angle 30 degrees. Absolutely. So over here, didn't mean to zoom out, but it'll be okay. I'm going to say that VAB, my line voltage, is simply VAN times √3 angle 30 degrees. So what do you think the relationship between VBC and VBN is going to be? I asked a question, somebody answer. I don't care if you're wrong, but somebody say something. Look for the relationship between VBN and VBC. So I hear they're the same. So VBC and VBN literally can't be the same voltage because they represent two different things. Caleb. Okay, so that's 100% correct. Using Kirchhoff's voltage law, we wrote a KVL equation around this path. We would very much find that VBC is equal to VBN minus VCN. That is what you said, right, Caleb? Which would be VBN times 1 minus 1 angle negative 120 degrees, because we know that the C phase lags the B phase by 120 degrees. And once again, that is simply a factor of √3 angle 30 degrees. So the relationship between our line voltage VBC and our phase voltage VBN is that you get the line voltage by multiplying the phase voltage by √3 angle 30. The exact same thing we saw for the A phase. Let me beat this horse to death. What is the relationship between VCA and VCN? You're making it too hard. What do I do to get from VCN to VCA? Multiply by √3 angle 30 degrees. The same damn thing I've done every other time, right? So we can use these relationships to convert any Y connected source into an equivalent delta connected source, because from the perspective of everything that is connected to it, it will only see what the line voltages are, right? So I am saying that if I have a Y connected source and I want to convert to a delta connected source, let me write these out here: VAN, VBN, VCN, VAB, VBC, and VCA. To go from Y to delta, I simply multiply by the square root of 3 angle 30 degrees. So my phase voltages for my Y connected source are transformed into my phase voltages for my delta connected source by multiplying by √3 angle 30 degrees. There really won't be any, actually, I take that back. We're very infrequently going to need to convert a Y source into a delta source because we're looking for a single phase equivalent circuit, which means we need our Y connected source. So how do you think we're going to go the other direction? If we have a delta connected source and we need a Y connected source, what are we going to do? Divide by the same damn thing or multiply by 1 over √3 angle 30 degrees, okay? So that √3 angle 30 degrees thing is our conversion to go from Y to delta. When we multiply by √3 angle 30, we're converting from Y to delta. When we divide by √3 angle 30, we're converting from delta to Y. So any delta connected source we face, we can make it look like a Y connected source by simply dividing the phase voltages by √3 angle 30 degrees. Okay. So this is our transformation between balanced sources. Now let's look at transformation between balanced loads. So I'm going to introduce you guys. You may have seen this before. I honestly don't know. I'm going to introduce you guys to a technique called a Y delta transformation for impedances. Okay. So let's say that I have a Y connected impedance. So here's A, B, N, and C. I'm going to call this ZYA, ZYB, ZYC. By the way, just as a heads up here, I am going to derive this relationship for an unbalanced load. So an unbalanced Y converting to an unbalanced delta and vice versa. And then we are going to apply that relationship to balanced load specifically. A bonus question for your upcoming exam on three-phase systems might be doing this transformation for an unbalanced system. So effectively, I'm telling you very explicitly, write down the equations that I'm about to give you, and you will get the bonus problem correct on your next test. All right, so what I have depicted here is a Y connected load and a delta connected load. And we are going to figure out how to replace the Y with a delta and the delta with a Y. And in order to do that, we are going to need effectively an equivalent impedance seen between the terminal pairs, right? So if I look at the Y connected load, what is the impedance that I see between terminals A and B? I'm sorry, what was that? No, so I'm just looking for an equivalent impedance. So if I look in between A and B, what do I see? ZYA plus ZYB. Absolutely right. If I look in between terminals B and C for my Y connected load, what am I going to see? YB plus YC, yep. And if I look in between terminals C and A, I'll see ZYC plus ZYA. Now, let's look at our delta connected load. If I look in through terminals A and B, what do I see? Not just Z delta A though. Right, so tell me what that's going to be. So that would be all three of them in series, which, right, so Z delta A is going to be in parallel with Z delta C plus Z delta B. Yeah. So I'll write it down the way that you're describing, which I don't much care for, and then I'll write it down the way that I like it. But it'll be okay. They're the same thing. I just don't like all those reciprocals. So if we look in through terminals B and C, we're going to have something pretty similar, right? We're going to see Z delta B in parallel with Z delta A in series with Z delta C. Oops, scroll too far. And similarly, looking through the C and A terminals is going to give us Z delta C times Z delta A plus Z delta B over that same denominator, Z delta A plus Z delta B plus Z delta C. So it may not look like it here, but I actually have a system of equations that I can solve, right? So if I know what my Y connected impedances are, I have three knowns. And then I have three unknowns that are my delta connected impedance, right? So I can develop a relationship between these two sides. And what I will find is that, so this is my Y to delta conversion. I'll find that Z delta A is equal to ZYA times ZYB, excuse me, plus ZYB times ZYC plus ZYC times ZYA divided by ZYA. Z delta B is going to be the exact same numerator, except divided by ZYB. And Z delta C follows the same pattern. Numerator remains the same, and the denominator changes to the C phase impedance. So before we move along to convert from delta to Y, which is what we're actually interested in here in a moment, let's think really quickly here about what would happen if all of our Y-connected impedances were the same. So ZYA, ZYB, and ZYC were equal. So if they're equal, that's going to look like ZY times ZY plus ZY times ZY plus ZY times ZY, or 3ZY squared, divided by ZY is just 3ZY. So for a balanced Y load, Z delta will literally just be 3 times larger than ZY. If we go the other way around, we'll find that ZYA is equal to Z delta A times Z delta C divided by Z delta A plus Z delta B plus Z delta C. Oops, this thing keeps scrolling too far on me. ZYB will be Z delta A, Z delta B over that same denominator, Z delta A plus Z delta B plus Z delta C. And finally, ZYC will be Z delta B, Z delta C over Z delta A plus Z delta B plus Z delta C. So if all of our delta connected impedances are the same, so Z delta A is equal to Z delta B is equal to Z delta C, then what we're going to have is Z delta times Z delta over 3Z delta, which is going to look like 1/3 Z delta. So effectively, for a balanced delta connected load, we get our Y equivalent by dividing the delta connected impedance by a factor of 3. We want to go the other way around, converting from Y to delta, we multiply by 3. So to summarize things, for a B, C, ZY, 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 A, B, C, Z delta, delta, delta. To go from Y to delta, we know that Z delta is 3 ZY. To go the other way around, we know that ZY is 1/3 Z delta. So, excuse me. Let's apply these relationships and analyze some circuits. So one of you guys tell me a configuration, right? So we have 4 different possibilities. We have a YY system, which we talked about last Thursday. For a YY system, we don't need to do any conversions whatsoever. Everything is already in the form that it needs to be to use the single phase equivalent circuit. Then we have a delta Y system where our source is delta, our Y is a load, which would require us to transform our source. We have a Y delta system, which means our source is Y, our load is delta, so we'd have to transform our load in order to use our single phase equivalent circuit. And then lastly, we have a delta delta system where our source is in delta and our load is in delta, and we have to convert both. So Lindy, tell me, give me a system. Literally just say delta Y, Y delta, or delta delta. Just choose one of those 3. Delta Y. Okay. So we're going to have a delta Y system. All right. So I'm going to draw that. So here's our delta connected source. This will be our A terminal, our B terminal, and our C terminal, which means this voltage is VAB. This voltage is VBC. And this voltage is VCA. I'm going to have transmission lines. Connecting my source to my load. So here's my capital A terminal, my capital B terminal, and my capital C terminal. Now I need a Y connected load. Like so. All right, so let's see what we're going to try to figure out. Okay. So let's say that our goal is to figure out these 2 quantities. Our line current IAA and our line voltage VAB. All right. So Matthew, give me an RMS phasor voltage. All right. So VAB is 120 angle 0 degrees. Volts RMS. Simon, give me a transmission line impedance, and the numbers are usually less than 1. So some real part, and then some imaginary part. The numbers are usually less than 1. I'm sorry, what was that? Yes. (0.5 plus J 0.5 ohms. Thank you. Grayson Schneibel, give me a load impedance. Real plus imaginary, yeah. All right. So you guys have made up this problem. Okay, I am going to show you how easy this is by simply converting from a delta connected source to a Y connected source, right? So how do we do that? If Matthew gave us VAB, we need VAN. What do we do? Go back in your notes, a page, page and a half. So because I'm going from delta to Y, I need to divide by √3 angle 30. Okay, so to go from delta to Y, we divide by √3 angle 30. So VAN is going to be 120 angle 0 degrees, volts RMS, divided by √3 angle 30 degrees. I don't know what 120 divided by the square root of 3 is off the top of my head, but I know the angle is going to be negative 30. $69.282 angle negative 30 degrees volts RMS. That is the only conversion that I need to do, and now I can draw my single phase equivalent circuit. For my single phase equivalent circuit, here's my A phase. Here's VAN. There's my neutral terminal, VW, VY. So using my single phase equivalent circuit, I can get the quantity IAA directly, right? So let's go ahead and solve for that really quick. Somebody tell me how we're going to do it. So current division requires us to have a known current splitting up between impedances in parallel, and we have the exact opposite. We have a known voltage and voltages or impedances in series. So I believe, if I'm understanding you guys correctly, we're going to divide that voltage VAN by those two impedances connected in series. I agree with that. Why is there a what? It's an A. My pen, or is it right here? That's an A. I just am writing terribly this morning. My apologies. Is that the one that? Oh, that's a lowercase n. I'm sorry. For my neutral connection on my source side. Yeah. That's a lowercase n. Yeah. So we always just make a short between our neutral, that's the lowercase n connection on our source side to the neutral capital N on the load side, because in a balanced three-phase system, we know that there is no voltage drop between our neutral connections, which is the same thing as what would happen if we had a short circuit there. All right, so we're going to have 69.282 angle negative 30 degrees volts RMS. I'm just going to add these numbers together. So 45.5 plus J 65.5. No, 45.5 plus J 62.5 ohms. 0.896 with an angle of negative 83.945 degrees. Amps RMS. If I wanted my line current IBB, what would I do? Subtract 120 degrees from the phase angle, right? I don't need to do any new math or anything like that. No new analysis. Okay. So we figured out half of the problem already. Great job. Now we need to figure out how we're going to get that line voltage at our load. Anybody have any thoughts? So that current times that wire impedance, that would give us, let me do this in orange because we haven't done this yet. This voltage VAA, how does that help? No, I want my line voltage, which would be the voltage VAB in green. I don't understand what you're suggesting. So v lowercase a lowercase b was given to us. We are trying to solve for v uppercase a uppercase b. Because there is a wire impedance in the way, the two things aren't directly in parallel, so there is going to be some voltage drop. So what do you mean by IAB? Let me start there. Okay, so I think what Caitlin is suggesting, I may be misrepresenting what she's suggesting, so if I am, please correct me. We know what IAA is. If we multiply IAA times this impedance ZY, we'll get this voltage VAN. If we multiply IBB, which we can get simply by shifting IAA times negative, or shifting it by negative 120 degrees, we could get this voltage VBN, right? And then we could write a little Kirchhoff's voltage law equation around that loop. So let's figure out what VAN is. So VAN is something that I can solve for directly using my single phase equivalent circuit, right? So how would I solve for VAN? Well, we'll do exactly what Caitlin suggested. IAA times ZY. So that'll be 0.896 angle negative 83.945 degrees amps times 45 plus J 62 ohms. Gives me 68.656 with an angle of negative 29.918 degrees volts RMS. From Caitlin's suggestion, we need VBN. What's that going to be? Yep. So 68.656 .656. Angle negative 149.918 degrees. Volts RMS. All right. So what do I do now? Absolutely right. VAB. Do it over here. So that would be 68.656 angle negative 29.918 degrees volts RMS minus 68.656 angle negative 149.918 degrees volts RMS. Comes out to be 118.916 angle 0.082 degrees volts RMS. So that was a long way around, but it absolutely worked. Okay. Anybody figure out what the short way is? Let's scroll way back up here. Way back up here. Here we go. So how did we go from phase voltage to line voltage here? We just multiplied the phase voltage by √3 angle 30 degrees. That is the exact same result that we would have gotten by saying VAN minus VBN. So there's absolutely nothing wrong with what Caitlin suggested, but we have proven over and over again, when we take the difference between two phase voltages to get a line voltage, it's the same thing as just multiplying the phase voltage by √3 angle 30. So just to prove it to yourself, multiply that voltage by √3 angle 30 degrees and see what you get. What you get? The exact same thing. It has to be. If the A phase and the B phase are separated by 120 degrees, it literally has to be that √3 angle 30 degree relationship. I'm trying to drill into you guys' brain. You don't have to get bogged down in the math with literally any of this crap. If you want to go, when you have a Y connected anything, you want to go from a phase voltage to a line voltage, just multiply by √3 angle 30 degrees. It has to work out that way, right? Once again, I want to reiterate, there is absolutely nothing wrong with what Caitlin did, because it's literally how we derived it. But at some point, I will annoy you into doing it my way and just multiply by √3 angle 30 to go one direction, divide by √3 angle 30 to go the other direction, instead of actually analyzing the circuit. All right, so we got our quantities of interest. Let's make up another problem. Somebody give me another type of configuration. Delta delta, okay? Oops. So this is A, B, and C. Then that makes this voltage VAB. That makes this voltage VBC. And this voltage is VCA. We are once again going to have transmission line ZW. Here will be our capital A terminal. All right, we have a delta connected load as well. Exactly right. Okay. So let's do something arguably difficult. Let's figure out what this phase current is. Yeah, that'll work. Just that one quantity. There are 2 or 3 different ways I can think of to do this. But we'll get to that in a minute. So let's see, Preston, give me a voltage. (140 angle 30). All right. Charles, give me a transmission line impedance. So once again, I'm expecting numbers for both the real and the imaginary part to be less than 1 usually. Yeah. Yes. All right. Catherine, give me a load impedance. I'm going to change it to J24 just because it'll make the math very slightly easier. So in order for me to draw my single phase equivalent circuit, I'm going to need to know VAN and what I'm going to call Z delta Y. So this is the Y equivalent of my delta connected impedance, right? So how do I get VAN if I have VAB? How did we do it 5 minutes ago? Am I multiplying or am I dividing? Divided, right. So when I have a line voltage and I want to go to a phase voltage in a Y, I divide by √3 angle 30. So that's going to be 140 angle 30 degrees volts RMS divided by √3 angle 30 degrees. Looks like 80.829 angle 0 degrees volts RMS. Okay. If I want to convert a delta connected load to a Y connected load, what do I do? One-third, right? So I divide by 3. Scroll up here to find it. ZY is going to be 1/3 times Z delta. So now it should be a little bit more obvious why I changed that 25 to a 24. 1/3 of 36 minus J24 looks to me like 12 minus J8. Oh, a nice even number. So from here, I can draw my single phase equivalent circuit. So here's A. Here's VAN. Here's EW. Here's the delta Y. Capital N like so. All right, so I have everything that goes into my single phase equivalent circuit. Now we need to talk about our options here. Okay. So there are two fairly straightforward ways that I can find that current IAB that I have labeled up there. And I just want you to be clear, that current does not exist on our single phase equivalent circuit, but we're going to use things that we can find on our single phase equivalent circuit to get it. Okay. So the two different ways that I can think of to solve for this thing is realizing that this current, let me draw it here using the colors that I've been using. This would be my phase current ICA. And this would be my line current IAA. And I can write a KCL equation. I'm going to do it here. So just call this KCL at A is going to look like IAA will be equal to IAB minus ICA. Everybody okay with that? Anybody have any problem with that relationship? And I know that IAB and ICA are related to each other. Like so. So that if I can find IAA, which I can absolutely find on my single phase equivalent circuit, I can now figure out what my phase current IAB is using this relationship. That's one way to do it. Another way to do it would be to simply divide my phase voltage VAB by my impedance Z delta. Well, how do we find that phase voltage VAB? The exact same way we did it in the previous problem, right? We could find the line to neutral voltage. VAN on here and multiply it by √3 angle 30. Both ways are going to give us the exact same result. So let's actually just prove that really quickly. So it doesn't matter which way you approach it. either by using KCL or by transforming voltages, you're going to wind up getting the exact same result. Okay. So what's my line current IAA going to be? How did we figure it out for the previous problem? Yep, sounds legit. So 80.829 angle 0 degrees volts RMS divided by, let's see, 12 plus 0.539, so 12.539, and then minus J8 plus 0.24 is going to be minus J7.76 ohms. My mental math is correct. If it's not, please tell me. All I did was add this number to this number. If I screwed it up, please let me know. So let's see. I get 5.481 angle 31.752 degrees amps RMS. Looking at my KCL relationship, I can then see that IAB simply IAA divided by 1 minus 1 angle negative 240 degrees. Looks like 3.165. Come on. There we go. Angle 61.752 degrees. Amps RMS. Anybody know what 1 minus 1 angle negative 240 is? Or 3 angle negative 30 degrees. Very similarly related things, but because we're going in the opposite direction, since we're going 2 phases instead of 1 phase, the angle turns out to be a negative quantity. So that is one way to solve for that quantity IAB. Now let's do the other way that I discussed. Find VAN, multiply VAN by √3 angle 30 to get VAB. Divide VAB by Z delta, we should get the exact same result. Okay. So VAN is going to be IAA times Z delta Y. So 5.481 angle 31.752 degrees. Amps RMS times 12 minus J8 ohms. Which I get to be 79.054 angle negative 1.938. From here, we could say that VAB is simply VAN times √3 angle 30 degrees Comes out to be 136.926. Angle 28.062. And IAB will simply be VAB divided by Z delta. So 136.926 angle 28.062 degrees volts divided by 36 minus J 24, right? Hold on. Comes out to be 3.165 angle 61.752 degrees. Amps RMS. So as we should expect, both ways give us literally the exact same. So this is a kind of a choose your own adventure type thing. All right. Let's do the in-class assignment now.